saying that you can't have two identical particles having the same state. Right? And based on that is, well, chemistry. Right? So if you have two particles in the inner layer, in a sense, of an atom, they don't have the same state. They may have certain parameters, certain portions of the state the same, but there'll always be at least one factor, one thing about the state that's different. And by having inner layers and outer layers, at each layer, the properties change, and there's like a limited number of possibilities. I'm being a bit vague here, but we need to know more quantum mechanics to explain. But there's a limited number of possibilities at a given level. And as you add more and more electrons, you fill up those possibilities. And then you have to go to a level further out from the nucleus, and where new possibilities will open up. But they too are a finite number, and they'll fill up, and so on. So you get this kind of hierarchy of layers, or orbits, if you like, of electrons around the nucleus. And that's how you build up the atomic table, Mendeleev's famous atomic table. That's how you get the elements. So the PEP, the Pauli exclusion principle, is fundamental to explaining the chemical table, table of the elements, the structure of the atoms, and ultimately chemical bonding, the whole of chemistry, which is essentially about the chemical bond, if you think about it. Otherwise it's physics. It would be sort of like physical chemistry. So chemistry is mostly about molecules, right? Study of molecules. And what are molecules? Well, they're just bonded atoms, right? So the PEP plays a deep role in all that. Okay. Now, just to finish off a bit, the PEP applies not only to electrons, it applies to protons, it applies to neutrons. So in the nucleus, you have that same kind of hierarchy of layers of the protons and neutrons within the nucleus, right? You get the same kind of structure. So then you might speculate, well, let's see, if you have chemical bonds between electrons, can you have a kind of chemistry at nucleon? A nucleon is just a collective name for a proton or a neutron. So can you have a kind of nuclear scale chemistry? Can you have nuclear bombs and that sort of stuff? That's another one of my interests that fascinates me. That's the possibility of a femtotech. A femto is just short for a femtometer. That's 1,000,000 times smaller than a nanometer. Today, nanotech, molecular scale engineering, that's all the rage. But I'm fascinated by the possibility of a femtotech. Could we have a kind of engineering and computing at the femto scale? Now, I've already dreamt up a way to compute, at least in principle, using femtometer scale creatures. I use quarks and gluons. Now, if you do particle physics, I'll give you 5 levels of courses of particle physics, starting at undergrad. In fact, I'm processing the book right now, just a minute. Here's the textbook at undergrad level on particle physics. It's just called Introduction to High Energy Physics. It's by, well, you probably can't see it, Donald Perkins, and it's you can probably see this here, 4th edition. That's a very good sign. So it's an excellent text, and gives undergrad level, senior. Well, it's probably senior M1. It's probably mix. It gives you a pretty good idea of what particle physics is all about. So, if you watch that, if you study that course on particle physics at undergrad level, well, senior M1 level, then you'll learn about particles can be divided into 2 broad categories. Those that have whose wave functions are antisymmetric, and they are called fermions, based after the Italian-American physicist, nuclear physicist Fermi. And the other category, those particles have symmetric wave functions. That category of particles, they're called bosons. Now you've probably heard of the Higgs boson, the famous particle just discovered a week or so back at the famous LHC, the world's highest, most expensive, highest energy particle accelerator in Geneva, in Switzerland, Large Hadron Collider. Okay, so two broad categories of particles, so the fermions and the bosons. And why the difference? Well, it depends on something called the spin. Now, we won't talk about spin until chapter 7. Now you can think of the electrons spinning around the nucleus. That's one way to conceive them. But the electrons and elementary particles themselves have a kind of intrinsic spin, like they spin around themselves. Well, that's a rather crude analogy, but yeah, it's good enough. Sort of like the way the Earth spins on its own axis, but the Earth also spins, orbits around the Sun. So you can imagine, visualize it if you like, the intrinsic spin of the electron. So it's spinning about its own orbit, an axis within itself, and it's also going around the nucleus, analogous to the planets and the Sun. Now that's awfully crude, but at least it gives you an intellectual handle to think about what spin is. Now it turns out that now I haven't written it here, I'll just say it. Now spin is also quantized, right? It's also part of quantum mechanics, and we'll study this in detail in chapter 7. On angular momentum, and a particular kind of angular momentum is spin. The mathematics is very similar, and it turns out that if the spin value, the quantized value, allowed values of the spin of a particle is half integer, like a half of a particular unit, or 3 halves of that unit, or 5 halves of that unit, such particles are called fermions, and they have anti-symmetric wave functions. And the other category, called bosons, their spins are integral of this unit, so 0 or 1 or 2. For example, the graviton, that's the quantized particle of gravity, gravitational field. Still a lot of people working on it, the graviton, the particle of gravity. It has spin 2. So it's a boson. And there are other particles of spin 1 and particles of spin 0. So they're all bosons. Now, the bosons do not obey the PEP, right? They do not obey the Pauli exclusion principle. So that means they can all congregate at the lowest energy levels. And just recently, Nobel Prize won for showing this phenomenon. So now experimentally, this has been done, but it required extreme cold to get this phenomenon to work. To get atoms condensing so that they behave as one system. Bosons. The technical term was a BE, that's Bose. That's the Indian theoretical physicist from which the term boson, a particle that obeys Bose, B-O-S-E, Indian statistics. And so Bose and Einstein collaborated and found a certain kind of statistics in statistical mechanics. I'm still debating, should I teach an undergrad course on statistical mechanics? I may do. Still debating. And the other kind of statistics, which is appropriate for fermions, is Fermi-Dirac statistics. So those two came up with statistics for fermions, for particles that have anti-symmetric wave functions. Anyway, so you're getting a taste of what's coming, right? So it's a very rich subfield of quantum mechanics. It's multi-particle systems, and I've just given you a taste of it. Okay, so that's the end of this the theory section of this lecture, lecture 4. The next one will be on three-dimensional scattering, which is very important for particle physics, because that's just what's happening in the Large Hadron Collider, the LHC. And the next portion will be on problem solving. Now, there are a lot of problems in the problem section at the end of the book. Davies book. So if I do a third or so, then that'll be quite a lot of problems. It'll be a long problem session. Okay, so I'll stop there. Ciao.